Welcome to today's problem-solving session. In this video, we'll tackle LeetCode problem number 599, titled Minimum Index Sum of Two Lists. This is a fun and engaging problem that tests your ability to work with arrays, hash maps, and efficient indexing. Let's dive in and explore the challenge together. In this problem, you are given two lists of strings, list 1 and list 2, where each string represents the name of a restaurant. These lists correspond to the favorite restaurants of two different individuals. The goal is to find the restaurants that are common to both lists and are considered common interests. For each common restaurant, we calculate the index sum, which is the sum of its positions in list 1 and list 2. Among all the common restaurants, we need to identify the ones with the smallest index sum. If there are multiple restaurants with the same minimum index sum, we include all of them in the output, and the order of the output does not matter. Additionally, the problem provides constraints on the size of the input, ensuring that the maximum length of each list is 1000 and each restaurant name has a maximum length of 30 characters. Importantly, all strings in both lists are guaranteed to be unique. Let's look at an example to better understand the problem. Suppose list 1 contains the restaurants Shogun, Tapioca Express, Burger King, and KFC, while list 2 contains Piatti, Shogun, and Burger King. Here, Shogun is the only restaurant that appears in both lists. It is found at index 0 in list 1 and index 1 in list 2, making its index sum 0 plus 1 is equal to 1. Since there are no other common restaurants, the output is simply Shogun. This demonstrates how we identify common restaurants and calculate their index sums to determine the result. In another example, consider list 1 with the same restaurants, but list 2 now contains KFC, Shogun, and Burger King. Here, we find two common restaurants, Shogun and Burger King. For Shogun, the index sum is 0 from list 1 and 1 from list 2, resulting in a total of 1. For Burger King, the index sum is 2 from list 1 and 2 from list 2, resulting in a total of 4. Since the index sum for Shogun is smaller than for Burger King, only Shogun is included in the output. Note that while KFC is also common, its index sum of 3 is still higher than that of Shogun, so it is not part of the result. Now, let's examine a case where multiple restaurants have the same minimum index sum. Suppose list 1 contains happy, sad, and good, while list 2 contains sad, happy, and good. Here, sad and happy are both common restaurants. For sad, the index sum is 1 from list 1 and 0 from list 2, giving a total of 1. Similarly, for happy, the index sum is 0 from list 1 and 1 from list 2, also giving a total of 1. Since both restaurants have the same minimum index sum, they are both included in the output. The result is sad, happy, and the order of these restaurants in the output does not matter. To wrap up, let's review some key constraints and edge cases. First, the lengths of list 1 and list 2 can range from 1 to 1000, and each restaurant name can be up to 30 characters long, containing only lowercase English letters and spaces. All strings in the lists are unique. For edge cases, if there are no common restaurants between the two lists, the output should be an empty list. If the lists each contain only one element and that element is the same, the output will simply be that element. Lastly, in cases where multiple restaurants share the same minimum index sum, all of them should be included in the output, regardless of order. It's also important to ensure the solution is efficient enough to handle the maximum input sizes effectively, as both lists can be quite large. To begin addressing this problem, we first consider the brute force approach. The intuition here is straightforward. For every restaurant in the first list, we check if it also exists in the second list. If it does, we calculate the sum of their indices, which gives us the index sum for that common restaurant. As we iterate, we keep track of the smallest index sum encountered and the corresponding restaurants. This method is simple, but it requires nested loops, one to go through each item in the first list, and another to search through the second list. This results in a time complexity of n squared, where n is the length of the longer list. While easy to implement, this approach becomes inefficient for larger inputs due to the quadratic growth in time. On the other hand, it has a minimal space requirement, as no additional data structures are used. The trade-off, therefore, is simplicity versus performance, especially when working with large datasets. Now, to overcome the inefficiency of the brute force method, we can adopt an optimized approach using a hash map. The key idea here is to use a hash map to store the restaurants in the first list as keys and their indices as values. This allows us to perform lookups in constant time, significantly reducing the need for nested iterations. By treating the problem as finding common keys between two lists while minimizing their index sum, the hash map becomes a powerful tool. The process involves creating this hash map for the first list, then iterating through the second list to check for matches in the hash map. When a match is found, we calculate the index sum, compare it to the current minimum, and update our result if necessary. This approach improves the time complexity to O, n plus m, where n and m are the lengths of the two lists. While we do use additional space for the hash map, the trade-off is worthwhile for the performance gain, making this approach much more scalable and efficient for larger inputs. Ultimately, the optimized approach using a hash map stands out as the best strategy for solving this problem. While the brute force method is easy to understand, its O, n squared, time complexity makes it impractical for larger input sizes. In contrast, the hash map solution reduces the time complexity to O, n plus m, making it far more efficient and suitable for scalability. The additional space required for the hash map is a reasonable trade-off given the significant improvement in performance. By leveraging the hash map for constant time lookups, this method eliminates redundant computations and directly addresses the problem requirements in a structured and efficient way. This balance of time efficiency and coding simplicity is why we chose the optimized approach as the preferred solution. In this problem, we are given two lists of strings, list 1 and list 2, where each string represents the name of a restaurant. The goal is to find common restaurants between the two lists, but there's an additional constraint: we need to find those common restaurants that have the smallest index sum. The index sum is calculated as the sum of the index of a restaurant in list 1 and its index in list 2. If multiple restaurants share the same smallest index sum, we return all of them. To approach this problem, we can start by understanding the input and output. The input consists of two lists of strings, which may not always be of equal lengths, and their indices are unique within each list. The output is a list of strings containing the common restaurants with the smallest index sum. A basic way to solve this is a brute force approach, where we iterate through all combinations of restaurants from both lists, calculate the index sum for each common restaurant, track the minimum index sum, and finally return all restaurants that achieve that minimum. However, this approach has inefficiencies, especially for larger lists, which we'll address with an optimized solution later. To improve efficiency, we can use an optimized algorithm that leverages a hash map. This reduces the time complexity significantly compared to the brute force approach. The first step is to build a hash map from list 1. As we traverse list 1, we store each restaurant as a key in the hash map, while its index is stored as the value. For example, if list 1 contains the restaurants Shogun, Tapioca Express, Burger King, KFC, the resulting hash map will associate each restaurant with its corresponding index: Shogun, 0, Tapioca Express, 1, Burger King, 2, KFC, 3. This setup allows us to perform efficient O1 lookups to check if a restaurant exists in list 1 and retrieve its index. Once the hash map is created, we can then focus on list 2. We traverse through list 2 to check for common restaurants by determining whether each restaurant exists in the hash map. This way, we avoid the nested loops of the brute force approach, making the algorithm more scalable. As we traverse list 2, whenever we find a restaurant that also exists in the hash map, we calculate its index sum. This is done by adding the index of the restaurant in list 2 to the index stored in the hash map for that restaurant. To keep track of the smallest index sum, we maintain two variables: min_sum to store the smallest index sum encountered so far, and result, a list to store the restaurants that achieve this minimum. If the current index sum is smaller than min_sum, we update min_sum and reset result to contain only the current restaurant. If the current index sum equals min_sum, we add the restaurant to the result list. After completing the traversal of list 2, the result list will hold all the common restaurants with the smallest index sum. By using this approach, we achieve a time complexity of O, n plus m, where n and m are the lengths of list 1 and list 2, respectively. Additionally, we can enhance efficiency further by skipping calculations for restaurants in list 2 if their index sum is already greater than the current min_sum. This ensures we're only focusing on relevant comparisons. When solving this problem, it's important to consider edge cases to ensure our solution is robust. First, if there are no common restaurants between list 1 and list 2, the output should simply be an empty list. On the other hand, if all restaurants in list 1 and list 2 are common, the output will include only those with the smallest index sum. The algorithm also handles cases where the two lists have unequal lengths, thanks to the way we traverse list 2 and use the hash map for lookups. In terms of data structures, we use a hash map to store the indices of list 1 for quick access, and a list to store the final result. The time complexity of O, n plus m, reflects the efficiency of traversing each list just once, while the space complexity of O, n, accounts for the storage of the hash map. Let's now illustrate the algorithm with an example. Suppose list 1 contains Shogun, Tapioca Express, Burger King, KFC, and list 2 contains KFC, Shogun, Burger King. We'll build the hash map and calculate the index sum step by step. To execute the algorithm for the given input, we first build the hash map for list 1. Each restaurant is stored as a key, with its index as the value, Shogun, 0, Tapioca Express, 1, Burger King, 2, KFC, 3. Next, we traverse list 2 and calculate index sums for any common restaurants. When we encounter KFC in list 2, we find it in the hash map with an index of 3 in list 1. Adding its index from list 2, 0, the index sum is 3. At this point, we set min_sum to 3, and result becomes KFC. Moving to Shogun, we find it in the hash map with an index of 0 in list 1. Adding its index from list 2, 1, the index sum is 1. Since 1 is smaller than the current min_sum, we update min_sum to 1 and reset result to Shogun. Finally, for Burger King, the index sum is 4, which is greater than min_sum, so we skip it. At the end of the traversal, result contains only Shogun. The final result for this example is Shogun, as it is the common restaurant with the smallest index sum. This output demonstrates the efficiency of the hash map approach, as we avoided redundant comparisons and directly focused on finding the minimum index sum. By leveraging a hash map and focusing on one list at a time, we reduced the computational complexity from O, n squared, in the brute force approach to O, n plus m. This makes the algorithm suitable for larger inputs, ensuring both correctness and scalability. This Python solution to LeetCode problem number 599 is efficient and clear. Here's a step-by-step breakdown. 1. Input preparation *. The function begins by creating a dictionary index_map that maps each restaurant name in list 1 to its index. This allows for constant time lookups of indices, which is crucial for efficiency. 2. Initialization *. Two variables are initialized, min_index_sum to keep track of the smallest index sum encountered so far, initialized to infinity, and result to store the list of restaurants with the smallest index sum. 3. Iterating through list 2 *. The function iterates over list 2 using enumerate, which provides both the index and the restaurant name. For each restaurant, it checks if the restaurant exists in index_map, i.e., it is common to both lists. If it is, the function calculates the index sum by adding the current index from list 2 and the corresponding index from list 1, retrieved from index_map. 4. Updating results * depending on the calculated index_sum. If it is smaller than the current min_index_sum, the function updates min_index_sum and resets the result list to contain only this restaurant. If it matches the current min_index_sum, the restaurant is added to the result list. 5. Return statement * After iterating through list 2, the function returns the result list, which contains all restaurants with the smallest index sum. This approach is efficient with a time complexity of approximately O, n plus m, where n and m are the lengths of list 1 and list 2, respectively. The dictionary lookup ensures that checking for common restaurants is fast, and the algorithm avoids unnecessary nested loops. This solution handles edge cases, such as no common restaurants, returns an empty list, and ties in index sums, returns all tied restaurants. Here, we start by importing the necessary Java utilities. Then, we define the class solution and the method findRestaurant, which takes two string arrays, list1 and list2, as inputs. The goal is to find the common restaurants with the smallest index sum. First, we create a hash map called indexMap to store the restaurants from list 1 along with their indices. This allows us to quickly check whether a restaurant from list 2 exists in list 1 and retrieve its index efficiently. Next, we initialize two variables, min_index_sum, which keeps track of the smallest index sum we've encountered so far, and result, a list to store the common restaurants that have this minimum index sum. Then, we iterate through list 2 using a for loop. For each restaurant in list 2, we check if it exists in index map. If it does, we calculate the index sum by adding the index of the restaurant in list 2 to its index from list 1. This prepares us to compare and determine if the current index sum is smaller than min index sum. If the calculated index sum is less than the current min index sum, we update min index sum to this new value. We also clear the result list to remove any previously stored restaurants, as the new minimum index sum takes precedence. Then, we add the current restaurant to the result list. On the other hand, if the index sum matches the min index sum, we simply add the restaurant to the result list without clearing it, since it shares the same minimum index sum. Finally, after completing the iteration through list 2, the method returns the result list, which contains all the common restaurants with the smallest index sum. This approach efficiently finds the solution by leveraging a hash map for constant time lookups and by minimizing redundant calculations. To solve the problem, we start with a simple example where we have two lists of restaurant names. The goal is to find the common restaurant with the smallest index sum. First, we create a dictionary called index_map to store the indices of each restaurant in list 1. This allows us to quickly look up the index of any restaurant in list 1. Here, the index_map is created as a mapping where each restaurant name is a key, and its corresponding index is the value. For example, Shogun is at index 0, Tapioca Express is at index 1, and so on. Next, we initialize two variables, min_index_sum is set to infinity as a placeholder for the smallest index sum we'll encounter, and result is an empty list that will eventually hold the restaurant or restaurants with the minimum index sum. Now, we iterate through list 2 to find common restaurants with list 1. In the first 3 iterations, we check Piatti, the Grill at Torrey Pines, and Hungry Hunter Steakhouse. None of these are found in index_map, so we simply move to the next restaurant. On the 4th iteration, we find Shogun in index_map. This means Shogun is a common restaurant. We calculate its index sum as the sum of its index in list 2, 3, and its index in list 1, 0, which equals 3. Since this is the smallest index sum we've seen so far, we update min_index_sum to 3 and set result to Shogun. After finishing the iterations, the final result is Shogun, which we return as the output. In this example, we have multiple common restaurants between the two lists. As before, we first create the index_map for list 1, where each restaurant is mapped to its index. The resulting dictionary is the same as before. We then initialize min_index_sum to infinity and result to an empty list to store our findings. With these preparations, we can start processing list 2 to find the common restaurants and calculate their index sums. As we iterate through list 2, the first restaurant we encounter is KFC, which is found in index_map. The index sum for KFC is calculated as 0 from list 2 and 3 from list 1, giving us a total of 3. Since this is the smallest index sum so far, we update min_index_sum to 3 and set result to KFC. Next, we check Shogun, which is also found in index_map. Its index sum is 1 from list 2 and 0 from list 1, for a total of 1. This is smaller than the current min_index_sum, so we update min_index_sum to 1 and set result to Shogun. Finally, we process Burger King, which is also common to both lists. Its index sum is 2 from both lists, giving a total of 4. However, since 4 is greater than the current min_index_sum, we do not update the result. The smallest index sum belongs to Shogun, so the final output is Shogun. In this example, the two lists do not have any restaurants in common. Following the same approach, we start by creating the index_map for list 1. This time, Shogun is at index 0 and Tapioca Express is at index 1, so our index_map reflects these mappings. We then initialize min_index_sum to infinity and result to an empty list. With these preparations complete, we begin iterating through list 2 to look for common restaurants. As we process list 2, we check each restaurant one by one. The first restaurant, Piatti, is not in index_map, so we move on. Similarly, the second restaurant, Hungry Hunter, is also not an index_map. Since we have now checked all restaurants in list 2 and found no matches in list 1, the result remains an empty list. This indicates there are no common restaurants between the two lists, and the final output is an empty list. To analyze the time complexity of the findRestaurant function, we begin with the first major step, building the index_map dictionary. Here, we iterate through all the elements in list 1, which has a size of n. For each element, we perform a constant time operation to add it to the dictionary. This results in a time complexity of O(n) for this step. Next, we move to the step where we iterate through list 2. This list has a size of m, and for each element, we check if it exists in the index_map dictionary. Since dictionary lookups are O(1) on average, this check, along with calculating the index sum and updating the result list, takes constant time per element. Iterating through all of list 2 therefore results in a time complexity of O(m). Combining these, the time complexity for these two steps is O(n plus m). Now, considering the overall time complexity, we simply add the complexities of the two major steps, O(n), for building the dictionary and O(m), for iterating through list 2. This gives us a total time complexity of O(n plus m), where n is the size of list 1 and m is the size of list 2. Shifting to space complexity, we start with the index_map dictionary. This dictionary stores all elements of list 1 as keys and their indices as values, requiring O(n) space. Additionally, the result list holds the common restaurants with the minimum index sum. In the worst case, all restaurants in list 2 could match the condition, requiring O(m) space. Other variables such as min_index_sum and loop variables take constant space, O(1). Therefore, the total space complexity is influenced by the dictionary and the result list. With these components in mind, the overall space complexity is determined by the dominant terms, O(n) for the dictionary and O(m) for the result list. Adding these together, we get a total space complexity of O(n plus m). To compare this with a brute force approach, a naive solution would involve iterating through every pair of elements in list 1 and list 2 to find common restaurants and calculate their index sums. This would result in O(n*m) time complexity, as we would perform O(m) operations for each of the n elements in list 1. However, its space complexity would be O(1), excluding the result storage. In contrast, the optimized approach we're analyzing reduces the time complexity to O(n plus m) by using a dictionary for constant time lookups. While the space complexity increases to O(n plus m), this trade-off is acceptable given the significant improvement in time efficiency. Let's now break down the best, average, and worst-case scenarios for this function. In the best case, list 2 contains no elements from list 1. Here, the function would only create the dictionary for list 1 and perform O(m) lookups in list 2, resulting in O(n plus m) time. In the average case, some elements from list 2 will match elements in list 1. This still involves creating the dictionary and performing lookups, maintaining a time complexity of O(n plus m). For the worst case, every element in list 2 matches an element in list 1, and all matches share the same minimum index sum. While the time complexity remains O(n plus m), the result list may grow to O(m) in size, making it the most memory-intensive scenario. To understand the big O reasoning behind these calculations, consider that creating the dictionary in step 1 requires O(n), as we add each element of list 1 once. Iterating through list 2 and performing constant time dictionary lookups takes O(m). Combining these two steps results in a total time complexity of O(n plus m). For space complexity, the dictionary stores up to O(n) elements, and in the worst case, the result list may store up to O(m) elements. These two terms dominate the space usage, leading to an overall space complexity of O(n plus m). This provides a mathematically clear justification for the efficiency of the current implementation. When solving this problem, there are a few common mistakes you should watch out for. First, using inefficient nested loops to find common elements and calculate their index sums. This approach has a time complexity of O(n*m) and can lead to performance issues, especially for large inputs, where a more optimal solution exists by leveraging hash maps. Hash maps reduce the time complexity to O(n plus m) and are far more efficient. Another mistake is failing to handle duplicates properly, assuming that the lists only contain unique entries. If there are duplicate restaurants in either list, it can lead to incorrect index sum calculations and ultimately an incorrect result. Next, it's important to compare index sums correctly. Using the wrong comparison operator, like greater than instead of greater than or equal to, can result in missing ties, which is critical because the problem often requires returning all restaurants with the minimum index sum, not just one. Lastly, not considering edge cases, such as one or both lists being empty or having no common restaurants, can cause runtime errors or incorrect outputs. Always account for these scenarios to ensure your solution is robust. Overcomplicating the solution is another pitfall to avoid. Adding unnecessary data structures or complex logic can make your code harder to read and debug, which is counterproductive, especially in an interview setting. Many problems like this one often have elegant solutions that are both simple and efficient. Instead, focus on the optimal approach, which involves using a hash map. By storing the indices of restaurants from one list in the hash map, you can iterate through the second list to compute index sums efficiently. This approach minimizes the time complexity to O, n plus m. Understanding this pattern of replacing nested loops with hash map lookups is invaluable, as it comes up frequently when working with intersections of two lists. During interviews, be ready to discuss the trade-offs of this approach, emphasizing how it outperforms the brute force method, especially for larger inputs. Additionally, make sure you bring up edge cases, like empty lists or no common elements, as this demonstrates your thoroughness. Lastly, highlight the trade-off between time and space. While the hash map approach requires O(n) additional space, it significantly improves runtime, which is often a worthwhile exchange in real-world scenarios. This problem shares similarities with several related problems, such as LeetCode 349, intersection of two arrays, LeetCode 350, intersection of two arrays 2, and LeetCode 1, 2 sum. These problems also involve finding intersections or combinations based on specific conditions, and solving them efficiently often requires similar techniques like hash maps or sorting. Another related problem is LeetCode 205, isomorphic strings, which relies on clever use of hash maps for efficient comparisons. In addition to the hash map approach, there are alternative methods worth noting. One such method is the two-pointer technique. By sorting both lists and using two pointers, you can identify common elements with minimum index sums. However, this approach introduces an O(n) log n time complexity due to the sorting step, making it less efficient than hashing. Another alternative is to use set intersection. With Python sets, you can quickly identify common elements and then compute their index sums. While this is simpler to implement, it's still less efficient than using hash maps and requires additional data structures. Each of these methods has its own trade-offs, so choosing the right approach depends on the constraints and requirements of the problem at hand. Great job solving this problem. To recap, we tackled the minimum index sum of two lists problem using efficient hash map techniques. Remember, these skills are invaluable for interviews and real-world problem solving. Keep practicing and stay curious. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!